Good morning, everyone. We will continue with mechanics with the last chapter, with chapter 11, about the angular momentum. And in this chapter, we're going to discuss a few topics, along which are the torque. So we will recall what is the definition of the torque, which we have seen in the previous chapter. We will define the angular momentum for a particle and for a system of particles. We will actually derive the Newton's second law for the case of rotational motion again. And then you will see if we have a rigid body that is rotating about a fixed axis, how can we define its angular momentum? And finally, we will derive a new conservation law, which is the conservation of angular momentum. So let's start first with the torque. We have seen and defined the torque in the previous chapter when we were describing and studying the rotational motion of a rigid body about a fixed axis. We have seen that the force F as a vector, which includes the direction and the magnitude, is not enough to tell us whether the force will produce or not a rotation. Because what matters more than the force itself is the point of application of the force. So if we are applying a force close to the rotation axis or far from the rotation axis, etc. And so this F was not enough. We had to take into account also the vector position of the point of application of the force. And so this is why we had to define a new quantity, which we called it the torque, as the vector product between the vector position of the point of application of the force R and the force itself F. Now the point at the question here, can we generalize more this definition and can we apply it to a particle? Actually, the answer is yes. Let's consider a particle. So if you just consider here that we have a particle, this is the particle, okay? And this particle is at a distance r from the origin. So the vector position of the particle, which we call it P here, is given by r. And let's assume that this particle is undergoing a circular path, okay, with respect to the point O, which is a fixed point, under the action of the force F. So let's say that F, it has arbitrary direction in space, so it could make a given angle phi with respect to the radial direction, with respect to the vector position, direction of the vector position of the particle. Then we can define actually the torque of the force F acting on the particle relative to the origin O, and it's given by tau equals R cross F. So it's the vector product between R. Now, in this case, R is the vector position of the particle and the force F, which is acting on this particle. And so at the end, we end up with exactly the same definition, but the only difference is that R now is not the point of application of the force, because we are not dealing with a rigid body, but we are dealing with a particle. And so R is the vector position of the particle. So this is it about the torque. Now, let's go on and to define the angular momentum. We have seen previously in chapter 9 that if we have a particle, a given particle, or two particles, let's say, okay, that are moving with the same speed. هاي البارتيكل ماشية بسبيد v وهاي البارتيكل أكبر منها, let's say هي أكبر, and ماشي with the same speed v. Okay? Now we said that لحتى نقدر نفرق بيناتهم بحاجة لquantity, okay? هاي quantity should include the mass, لحتى لأنه الماس هي اللي بتقلي أي بتفرق بيناتهم, وكمان it include the speed m and v. وقت قلنا أنه في عنا الكاينتيك energy, والكاينتيك energy هي عبارة عن half mv squared. So it includes the information on both the mass and the speed. But this is not enough. Why? Because the kinetic energy is a scalar quantity. هي عبارة عن رقم وما بتخبرنا فعليا بأي اتجاه البارتكلز ماشيين. And so this is why we define the linear momentum P as the product between the mass and the velocity v. And we said that the direction of the linear momentum is definitely and of course defined by the direction of the vector velocity v. Now, in this case, when we are dealing with a particle that is making a rotational motion, so it's rotating about a fixed point, or it's undergoing a circular path about a fixed point. هل P عفوا هل بتكفي انه تعملنا description لشو عم بيصير؟ No, because actually we have seen from the previous chapter that a particle, we can describe the rotational motion of a given particle depending on the distance between the particle and the axis of rotation. فبالتالي بحالة البارتيكل إذا كانت عم تعمل rotational motion وعم تبرم حوالي بوينت معين، هيدي البي ما بقى تكفي كمعلومة، لأنه مش بس الفيلوسيتي هي اللي نحن بتهمنا نعرفها أو البي عموما، بس كمان يلي بيأثر بروتيشنال موشن هو قد ايه الديستنس ما بين هالبارتيكل وما بين البوينت او حوالي اللي عم تبرم حوالي. And so this is why we have to include R and P, both these informations. And so this is why we define what is the what we call the analog of the linear momentum. يعني شو equivalent للlinear momentum بالrotational motion؟ صح سميه angular momentum مثل ما سمينا variables اللي قبل angular speed, angular position, etc. And this angular momentum is defined as the vector product between the vector position r of the particle and the linear momentum of the particle. So as you can see here we have two vectors, and if we replace P as equal to m times v, وبما انه الm هي عباره عن scalar بتطلع لبرا يبقى m times r cross v. And so actually if you can also see, it's quite easy to see that L has the same definition as the torque. يعني بالحالتين سواء بالتورك او بالانجلر مومنتم عم ناخذ بعين الاعتبار البوزيشن للبارتيكل من خلال الفيكتور برودكت مع الفيكتور الثاني اللي هو بهمنا. باول حاله نحن كنا عم نشوف شو تاثير الفورس على الموشن للبارتيكل، فلهالسبب حطينا هون R كروس F. اما بثاني حاله احنا عم نشوف كيف البارتيكل والموشن تبعولها كان بي ديسكرايبد من خلال البوزيشن يلي لها ومن خلال اللينير مومنتوم يلي لها. بس طبعا اللينير مومنتوم منه كافي لانه we have to take into account هيدي الديستنس. So this is why we end up with R cross P. يعني هون بهالحاله حطينا ال P. Okay, now since L is a vector, so it has direction and a magnitude. The direction لل L هي على طول perpendicular to the plane that is formed by the two vectors R and P. In this example, we have R and P, they are both in the X and Y plane. البارتيكل M موجودة بالX Y plane بهذا البلين مثل ما نكون شايفين. اوكي وبالتالي الفيكتور R هي بقلب هذا البلين، وما انه البارتيكل M ماشية in a given direction فكمان ال P بهذا البلين. So this is why بما انه ال L هي الفيكتور برودكت ما بيناتهم بكون it's always perpendicular to the plane that is formed by these two vectors. وهالبلين هو XY، الperpendicular على ال XY هو ال X Z. And so this is why, for example, in this particular case, the angular momentum L of this particle, which is equal to R cross P, is along the Z axis. And the magnitude of the angular momentum is given by, so the magnitude of the first vector times the magnitude of the second vector times sine of the angle between the two vectors. يعني هون عمليا إذا ما نجي نحط ال L بقيمتها هيك ما نقول هي عبارة عن the magnitude of the first vector اللي هو ال R and then the magnitude of the second vector اللي هو ال MV. طبعا ال M is a scalar فبتطلع لبرا multiplied by sine of the angle ما بين ال R وما بين ال V عمليا أو ال P، بس هي ال P عندها أصلا direction لل V. So have a look هون شو هي الانجل ما بين البي وما بين الار. سو هاف ا لوك لحتى تعرفوا كيف هي الدايركشن. اول شيء بتمدوا اول فيكتور اللي هو الار، اول فيكتور بوصد فيها اول فيكتور موجود بالفيكتور برودكت، فبتمدوا اللاين تبعوله وبعدين بتشوفوا شو الانجل ما بين البي وما بين الار، فبيطلع معكم هذا هو الانجل فاي. فاذا هيدي هي عباره عن الفاي. الماجنتيود اوف ار هي ار بكل بساطه، الماجنتيود اوف ام في هي ام وفي. And then so you end up with m times v times sine phi. Okay, don't forget that L, it depends on the choice of the point P. يعني انتوا لما تجيبوا angular momentum, you're always defining the angular momentum with respect to a point, with respect to a fixed point, an origin. اللي هو بهالحالة this is our point we are looking at, and this is the point with respect to which the particle is moving, or it's making a circular path. Well, the unit of the angular momentum is kilogram meter squared per second. So in this spirit, we can define the angular momentum, which is the counterpart of the linear momentum in rotation. يعني هي equivalent للlinear momentum P بحالة البارتيكل كانت عم تمشي circular path أو عم تعمل rotation about a fixed point. Now, can we derive a Newton's second law for rotation using this definition of the angular momentum? Let's see. يعني احنا شفنا chapter 9, we have seen that instead of writing down the Newton's second law as we have seen it in its basic form, F net equals to ma, we have seen that when we defined the linear momentum, that we can write down this Newton's second law as, instead of writing down m times a, we could write down the derivative of the linear momentum with respect to time. So the question is, can we derive something similar to this Newton's second law, but in the case of rotation? طيب بالمبدأ yes. وعمليا احنا فينا نعمل guess لشو ممكن تكون الاكسبريشن لهيدي الايكويشن, and we are going to do it together. So نحن شفنا انه في equivalence او correspondence somehow ما بين linear variables والangular variables, وشفنا كمان انه يعني حتى بالchapter 10 شفنا انه الايكوفالنس لهيدي الايكويشنز given by الاف الايكوفالنس لها هي تاو, فبتصير تاو net is equal to الام الايكوفالنت لها هي المومنت اوف انيرشيا, هي الماس ديستريبيوشن, وبدل الاي بتصير الفا, right? So بنفس المنطق فينا نجي نعمل guess لشو ممكن تكون الايكويشن الجديده. Instead of force we talk about torque, so we can write down tau net is equal to a derivative with respect to time of what is the equivalent or the analog of the linear momentum. بعدنا شايفينه قبل شوي, هو عباره عن the angular momentum L. So instead of P we expect to have here L, and so we end up with this equation as the Newton's second law for the rotation. But we are going to see, to check together. Okay, so let's consider a particle which has a mass m and linear momentum p, and it's moving. Okay, so we know from the Newton's second law that sum of f is equal to the derivative of the linear momentum with respect to time. Now إذا بنجي هلا بنضرب هذا الإيكويشن من الشمال from the left hand side, if you just multiply it by r and then we make the vector product between r and the quantity which are in this equation, quantities, يطلع معنا انه r vector product of cross sum of f is equal to r cross the derivative of p with respect to time. كل شيء عملناه انه هون جينا حطينا r cross من الجهتين and then r cross. Okay, so we end up with this equation. Now هون في عنا r cross dp dt plus نحن هون إذا زدنا صفر ما بيتغير شيء. Okay, and this term is simply equal to zero. يعني بمعنى آخر عم نقول إنه هون أنا في عندي جزء, إذا بدي أجي أفكر بهيدي الريليشن ك derivative with respect to time of r cross p. Okay, الشيء اللي موجود هون هو جزء منه. هيدي الإيكويشن it gives back, هيدي بتعطينا dr dt cross p, okay, plus r cross dp dt. فاللي عندنا اياه بهيدي الايكويشن هون هو بس جزء منها اللي هو هالجزء, فنحن جينا ضفنا عليها الجزء الثاني وقدرنا نعمل هيدا الشيء من دون ما يكون في مشكله, لانه هيدا الجزء الثاني هو بكل بساطه صفر. ليه صفر؟ للي ما عرف what is the r dt? the r dt هي ال v, صح؟ هي ال velocity. By definition the definition of the velocity vector is the derivative with respect to time of the vector position. And then ال p هي شو, هي عباره عن m v. طيب that gives you m v cross v. The vector product ل two vectors which is the same vector, يعني الفيكتور مع حاله هو صفر بكل بساطه. وليش هو صفر؟ لانه قيمه هيدا الفيكتور برودكت هو عباره عن v اللي هي the magnitude of the first vector times the magnitude of the second vector multiplied by sine of the angle between the two vectors. وانه عم نحكي عن الفيكتور نفسه الانجل مع حاله هو صفر والساين للصفر هو صفر. اوكي سو بهالشكل نحن دخلنا صفر على الايكويشن، بس هالصفر هو هيدي هي قيمته، او قيمه الصفر هو بكل بساطه دي ار دي تي كروس بي. سو فينا نجمعهم اثنيناتهم ونحطهم بهالشكل هيدا، يعني هي the derivative with respect to time of r cross b من ناحيه، ومن ناحيه ثانيه هون ال r cross sum of f فينا نحطها هي as sum of r cross f. اوكي so اول شيء ال r cross f as we have seen in the first slide هيدا هي ماشي غير التورك تاو. اوكي وال r cross b هي كمان بكل بساطه the angular momentum L. And so we end up with sum of tau من أول part of the equation من the left hand side is equal to the derivative of the angular momentum of the particle with respect to time. And so we end up with this equation in here. Sum of tau is equal to the derivative of the angular momentum with respect to time. وهيدي فعلا هي الشيء اللي وصلنا له قبل اللي هون قلناه انه tau net is equal to the derivative of the angular momentum with respect to time. So in other words, the torque acting on a given particle is equal to the time rate of change of the particle's angular momentum. And be careful that this equation is only valid if sum of tau and the angular momentum are both measured about the same origin. Again, we have seen إنه التورك هي عبارة عن R cross F لما تكون البارتيكل عم تعمل rotational motion about a fixed point under the action of F. So tau, it's measured always with respect to some point, and L is also measured with respect to some point. So don't forget this. If you take the definition of L with respect to a given origin, which is different than the origin about which you define or you measure your torque, بصير غلط. يعني إذا كان في عندكم particle عم تبرم بالنسبة ل given point O, both tau and L should be measured with respect to this O. And finally, the angular momentum L, which is defined now as the vector product between the vector position of the particle and the linear momentum of the particle, should play the same role in rotational motion as the linear momentum P plays in translational motion. ومن هون we expect that we should have some conservation law for the angular momentum. لأنه نحن شفنا أنه بحالة linear momentum, if you still remember when we talked about the collision, شفنا انه we could get a conservation law للlinear momentum. شفنا انه من خلال هيدي الايكويشن F net equals dp dt. اذا ال F net equals to 0, then the derivative of the linear momentum with respect to time is equal to 0, يعني p is constant. So this is why here as well we will see that we can end up with the same conservation law. بس قبل ما نروح لهون ما ننسى انه كل الدسكشن اللي عملناها لحد هلا هي discussion about particle. يعني شفنا شو هي التاو for a force which is acting on a particle, what is the angular momentum of a particle. But now what if we have a system of particles, كيف بيتغير الدسكشن او كيف شو الايكويشنز اللي بيطلعوا معنا بهالحال. Okay, so let's say that we have a given system of particles. فينا ناخذ هذا البادي. Okay, we can say that this body هو عباره عن system of particles مؤلف من infinite number of particles or n number of particles. And so the angular momentum for this body, for this system of particles, which we call it capital L, relative to an origin, is defined as the vector sum of the angular momentum L of the individual particles. And we can take particle 1, particle 2, particle 3, particle 4, 5, 6, etc. up to a given number n of particles. فإذا هي عبارة عن L1 plus L2 plus L3 etc. plus Ln. And of course كل هيدول الانجلر momentum for individual particles, they are measured with respect to the same origin around which these particles are moving. And so this is nothing else than the summation of Li. I goes or runs from 1 up to n, where n is the number of particles that constitute this object, this system of particles. Then now, of course, since the angular momentum of this individual particle can vary as a function of time, مع انه هول البارتيكلز عم يتعرضوا لانتراكشن بالداخل وبالخارج. يعني الانتراكشن internal interactions هن ناتجه عن الانتراكشن ما بين البارتيكلز بين بعضهم، والاكسترنال انتراكشن هي ما بين البارتكلز بقلب السيستم واي شيء خارج عن السيستم. فنتيجه هالانتراكشنز internal and external, the angular momentum of the particles may vary as a function of time. And if they vary as a function of time, then we have to consider the variation of the total angular momentum L when such perturbations occur in the system with respect to time. So the derivative of L with respect to time is the derivative with respect to time of. We replace L by sum over I of Li. نجي بس بنحطها بقيمتها، هي عبارة عن summation Li over I, right? And so this is nothing else than the summation over I of, طبعا the derivative it acts only on the angular momentum وبالتالي هي derivative of Li with respect to time. But again, if you just get back to the previous slide, احنا شفنا قبل شوي انه we could find that tau net when a particle is acted upon by different forces, we can get the Newton's second law for rotation as given by sum tau net اللي هي sum of taus is equal to the derivative with respect to time of the angular momentum of the particle, right? فبالتالي اللي هي التاو نت محل الدي ال اي دي تي رح نحط تاو نت and so we end up with مثل ما هون ما شايفين derivative of Li with respect to time هي تاو نت I، يعني هي عبارة عن مجموعة التوركس يلي عم تتعرض لهم البارتيكل number I. And so we can finally write down the derivative of the angular momentum with respect to time. It's given by the summation over I of tau net I. هلا شو هي التاو نت I وشو بتتضمن؟ مثل ما شفنا قبل شوي انه هالparticles they are interacting between each others and they are interacting with the external surrounding. And so this tau net it includes both internal and external interactions. This is why this tau net it includes the torques associated with internal forces between the particles and the torques associated with external forces. But احنا بنعرف من Newton's third law انه اذا في عنا two particles which are interacting with each other، إذا الأولى عم تعمل force على الثانية بهالاتجاه and let's call this F1 applied on 2, then the particle 2 will apply a force F2 on 1 which has the same magnitude but opposite in directions, right? بشكل إنه F12 plus F21 are equal to 0. So التورك لهالاثنين حيكونوا نفس الشيء، يعني بنقدر نكتب انه كمان تاو 1 2 plus تاو 2 1 is equal to 0، وبالتالي كل هول التوركس هنا يجين عن الانترنال فورسز ما بين البارتكلز they cancel out، وما بيبقى عندنا غير بس التورك اللي هنا يجين عن الفورسز external على السيستم، يعني هنا بين البارتكلز of the system and the external surrounding. And so this is why هون ما بيبقى من التاو نت اي غير الاكسترنال torques. And so this is why we can write down the derivative of the angular momentum of a system of particles with respect to time. It's given by tau net, or in other words, the net external torque acting on a system of particles about an axis through a given origin, it equals the time rate of change of the total angular momentum of the system L about that origin. يعني عمليا عقد ما التورك كبيرة عقد ما بتكون الفاريشن للانجولار momentum L of this system of particles كبير. And vice versa. Now let's consider the case of a rigid body and let's see how can we write down the angular momentum of a rotating rigid body. ناخذ هذا rigid body, it's kind of a disc, or you can think about it بأي شكل من الأشكال. خلينا ناخذه بهذا الشكل نحن. And let's consider one of the particles which constitute the system. يعني هالسيستم اللي هو disc بهالحالة مثل ما شايفينه هو عبارة مؤلف عن given n number of particles, and so we can divide this object into elements, into mass elements. رح نسمي كل وحدة كل particle بتألفه هي عبارة عن mi, and each particle mi هي عمليا موجودة على بعد ri من الأوريجين اللي هو بهالحالة this is the point O we are talking about, and it's moving with speed vi, where of course we know that vi is tangent to the circle along which the particle is moving. يعني vi and ri they are perpendicular. okay? Now, if you want to get the angular momentum of this rotating rigid body, we are going to apply the definition that we have seen earlier. اللي هي إنه total angular momentum of a system of particle is the summation of Li, where I, it runs over the number of particles from 1 up to n. So now, if you want to determine total angular momentum L, we have to determine what is Li, okay? So let's take this particle as an example. From the definition of the angular momentum of a particle, we know that Li is equal to the vector product between the vector position of the particle, Ri, and the linear momentum of the particle, Pi. ما انه هون عم نحكي عن الماgnitude, so I just have taken the magnitude of this cross product. ومثل ما بنعرف هو عباره عن Ri, the magnitude of the first vector, multiplied by the magnitude of the second vector اللي هو m times or mi times vi, multiplied by sine of the angle ما بين ال r وما بين ال v. طيب نحن بنعرف انه حيلا for any particle that is moving along a circle, you always have the velocity vector is tangent to the circle, which means it's perpendicular to the radius. يعني الانجل ما بين ال r وما بين ال v هو عباره عن 90 degree. And sine of 90 degree is simply equals 1. And so we end up with Li equals Ri times Mi times Vi. And don't forget, just to complete our discussion, that the direction of the angular momentum in this case is along the z-axis. يعني بهالحالة Li الناتج عن هالبرودكت عنده direction along the z-axis. So Li ما عندها components غير Lz عمليا. So this is Li for a given particle of mass Mi moving along a circle of radius Ri with a given speed Vi. If you want to get now L total, we have to sum up all these individual angular momentum. And so we end up with sum over I of Li. So it's equal to the sum over I of Ri Mi times Vi. But now since the object is making a rotation, يعني معناتها انه كل البارتكلز okay they have different speed vi, linear speed, but they have the same angular speed omega. يعني نحن شفنا انه when we are dealing with a rigid body rotating about a fixed axis, rigid body يعني non-deformable, all the particles they move with exactly the same angular speed. And so we can write down vi as Ri multiplied by omega. So if we replace Vi by its expression, Ri مع Ri بتصير Ri squared. So we end up with sum over I of Mi Ri squared multiplied by omega. The summation هون doesn't include omega لأنه omega is the same for all particles. So تطلع out of the sum. But actually, if you just have a look at this expression, and if you still remember, the moment of inertia of a given rigid body is defined by sum over I of Mi Ri squared. هذا الشيء شفناه بالشابتر 10 كمان لما حكينا عن الروتيشن عموما. قلنا انه البديل عن الماس هو distribution of the mass about a fixed axis, about a given axis. And so if we replace sum over I of Mi times Ri squared by the moment of inertia I, then we end up with L equals to I omega. And so the angular momentum of a rotating rigid body, it can be written as the product between the moment of inertia of the body about that axis, the axis of rotation, multiplied by the angular speed omega. So this is it for the angular momentum of a rotating rigid body. Now, can we actually derive now the Newton's second law from this definition? That's the question. Let's try to do it. The variation of L with respect to time, okay, it's given by بنحط محل ال قيمتها اللي هي ال I times omega. فبيطلع معنا ال I, it doesn't change as a function of time لأنه نحن قلنا إنه we are dealing with rigid body والmass distribution لهالبادي ما عم تتغير مع الوقت، فبالتالي ال I بتضلها هي نفسها. يعني ال particles ما عم بيغيروا ال locations تبعولن with respect to each other and also with respect to the axis of rotation. So this is why the derivative is only for omega. So we end up with I, derivative of omega with respect to time. And by definition, this is nothing else than the angular acceleration alpha. The definition of angular acceleration here, the derivative of the angular speed with respect to time. And so we end up with I alpha. احنا شفنا قبل شوي لما حكينا عن Newton's second law for rotation, we have seen that we can write down tau net as the derivative of the angular momentum L with respect to time. Now, if the derivative of L with respect to time is nothing else than I alpha, that sounds great. Then we obtain again that tau net is equal to I alpha, اللي هي Newton's second law اللي جبناها بالchapter الماضي. And so the net external torque acting on a rigid body rotating about a fixed axis equals the moment of inertia of the body about that rotation axis multiplied by the object's angular acceleration relative to the axis. So we end up again with the same Newton's second law, بس هالمرة جبناها من خلال الديفينيشن والاكسبريشن لل يلي وصلنا له when applying the definition of L on a rotating rigid object اللي هي L equals to I omega. So before to come to the end, we have just to discuss one more thing, is that مثل ما شفنا بالchapter 9 شفنا انه لما حكينا عن linear momentum شفنا انه linear momentum it is very useful because it leads to a new conservation law. شفنا انه Newton's second law فينا نكتبها بشكل كثير general اكثر general اللي هو F net equals to the derivative of the linear momentum with respect to time. And then we said that if the system is isolated معناتها ما في external forces ما في exchange أو interchange أو interaction ما بين particles of the system and the surrounding environment, and so F net is equal to 0. معناتها the derivative of P with respect to time is equal to 0. معناتها P is equal to a constant, right? وبالتالي P initial is equal to P final. هون هنقدر نعمل نفس الشيء, but instead of using the Newton's second law for translation, we're going to use Newton's second law for rotation. And this Newton's second law for rotation will allow us to derive a new conservation law. احنا شفنا انه if you have a system of particles and you can actually say that the net torque exerted or acting on the system of particles is equal to the rate time of change time rate of change of this angular momentum of the system as a function of time. Now, what if the system is isolated? إذا كان السيستم isolated يعني ما في أصلاً ما في external forces acting on it لأنه ما في interaction ما بينه وما بين العالم الخارجي, and so tau net is equal to 0. Therefore, this means that the derivative of هون سميتها L total just to say that we are dealing with a system of particles. L total with respect the derivative of L total with respect to time is equal to 0. وإذا كان شغلة ما عم تتغير مع الوقت معناتها هي constant. That means that L total is equal to a constant. And so this is the new conservation law, which is the conservation of angular momentum. Whenever you have a system which is isolated, then we can immediately deduce that its angular momentum is conserved. يعني L is constant أو L initial is equal to L final, just like its linear momentum also is conserved, or in other words, P is equal to a constant. And so this is it. This is the third law of conservation اللي عنا إياها. أول conservation law هي كانت about the energy. If you have an isolated system, then its energy will be conserved. تاني conservation law شفناها هي conservation of the linear momentum. وثالث conservation law اللي هون طلعناها هي conservation of the angular momentum. So we'll end up with 3 conservation law for an isolated system. And if we consider a system actually where the mass is isolated, so the mass is changing as a function of time. So let's consider an isolated system, and the system is rotating about some given axis. And if the mass of this system is changing as a function of time, in other words, it undergoes a redistribution in some way. يعني مثلا مثل هون الإكزامبل في عندكم student قاعد على كرسي وحامل بايديه طاول الاوزان. اذا فتح ايديه باول بانيشال ستيت وبعدين رجع ضبهم لايديه بشكل انه صاروا هدول الاوبجكتس قدامه. بهالطريقه عم بيصير في redistribution of the mass, لانه هون هيدي الماس كانت على بعد let's say r I من الاكسس اوف روتيشن, بينما هون بطلت على بعد RI من الاكس اوف روتيشن، صارت at very small distance with respect to the axis of rotation. فهذا بنسميه redistribution of the mass. And so in this case the system's moment of inertia changes لأنه ما بين هيدا السيتويشن وما بين هاي السيتويشن the moment of inertia is different. And so بما انه في عندنا conservation of the angular momentum بحكم انه هذا السيستم اللي هو الشخص مع الكرسي عباره عن isolated system، بما انه عندنا ال conservation of L، فاذا الاي تغيرت حكما الاوميجا بتتغير، ولهالسبب لما يضب ايديه بصير السرعه اكبر. So a change in the moment of inertia I for an isolated system requires a change in omega definitely. لأنه لما نقول إنه Li is equal to Lf, the angular momentum in the initial state is equal to the angular momentum in the final state. And since the angular momentum is defined as I times omega, so we can replace or substitute Li by I omega I اللي هي بالinitial state is equal to If omega F. So if I in the initial state is different than I in the final state, then حكما the omega initial will be different than omega final. Okay? هذا الشيء اللي بقلنا عنه conservation law. And the last slide for this chapter and for the mechanics also, I just want to recall and remind you of the corresponding between or correspondence between the different variables that we have seen. يعني احنا بالقبل حكينا بشكل كتير موسع عن اللينير variables لما حكينا عن translation من اول الميكانكس لوصلنا للاخير للchapter 9 where we have seen the position وعرفنا displacement وبعدين عرفنا velocity and the acceleration based on this displacement. Then we have seen انه لما ناخذ بعين الاعتبار الماس m of a particle, then we go to the dynamics and then we talk about the force. All this allows us also to talk about the kinetic energy بمكان ما, linear momentum, وكمان شفنا نيوتن's second law باشكالها الاثنين, F equals to ma وال F كمان equals the derivative of the momentum with respect to time. Now in this table you will find all these equivalent or analog variables. The halt of the rotational motion, which we call them angular. So instead of x, we talked about the angular position theta. Instead of delta x, we talked about the angular displacement delta theta. Instead of the velocity, we talked about the angular speed omega. Instead of a, we defined the angular acceleration. وهون بدل ما نحكي عن الm حكينا عن the moment of inertia. So we talked about the moment of inertia اللي هي مش عبارة عن m, هي عبارة عن distribution of the mass along or about the rotational axis. شفنا انه ما بكفي بس نحكي عن الفورس بالروتيشنال موشن، وانما لازم ناخذ بعين الاعتبار زياده عن المعلومات الموجوده بالفيكتور F هو البوينت اوف ابليكيشن اوف ذا فورس F. لهالسبب اضطرينا انه نستخدم a new variable او a new concept اللي هو التورك. kinetic energy كمان مثل ما عندنا kinetic energy for translation عندنا kinetic energy for rotation which is equal to half I omega squared. وبكل مكان كنا عم نشوف قد ايه في correspondence ما بين الاشكال الفورم تبع هيدي الديفينيشنز. يعني هون نقدر نستنتج انه الK for rotation is equal to half الايكوفالنت للماس نحن بنعرف انه هي المومنت اوف inertia I والايكوفالنت للV هي الانجلر سبيد omega squared. And so we can immediately deduce all the equations and the definitions that we need in the angular or in the case of rotational motion بس من خلال نعمل correspondence ما بين linear وال angular variables. So the analog of the linear momentum is the angular momentum. مثل ما ال P equals ل M times V, ال L هي equal لل I times omega, ال I هي ال equivalent لل M وال omega هي equivalent لل V, etc. etc. And so finally, just also like we have seen that the power بمكان ما عرفناها بالchapter 9 إنه هي the scalar product between F and V. Also, we can write down the power is equal to the torque multiplied by the angular speed omega. And so this is it for this chapter and for the mechanics part. We still have to solve the problems in chapter 11.